A little more calculus review for today. Let's copy all of that. All right, so a couple key words here. In the last part here, we are trying to find the rate of growth 9 days in. So if I is the number of people, and then we find the derivative with respect to t of our function I, right? So that's the rate of change of the number of people infected, right? Our change in y. So delta y. I'm gonna move some of my Zoom stuff out of the way. No. Over delta x, or delta t in this case. So change in y over change in time. And our y is the number of infected people. So that's a change in people. Change in people divided by change in days. So when we calculate the derivative, when we evaluate it, we're always going to get people per day. So we talked about the appropriate units. So it's always good to note that whenever you're doing an actual rate of change problem, what that's measured in. And then from there, it's just take the derivative. And so we know the derivative of e to a power is e to the power, and then the chain rule kicks in because that's more than just a t up there. So I want the derivative with respect to time, 5,000 times e to the power 0.079 t. And the 0.079, that's approximately the daily growth rate in an exponential problem like this. If that number up there is relatively small, then it turns out that the population is increasing, because that's a positive number, at about 7.9% per day. As an interpretation of that. It's not exactly that, but it's close. And you may have seen that in a college algebra class, hopefully. So 5,000 is a constant, that just tags along. Derivative of e to a power is e to the power. And then the chain rule says anytime you don't have just an x or just a t here, you got to multiply by the derivative of this right here. And the derivative of that power is just that value, 0.079. So that's the derivative. We could clean it up by multiplying those two together. So calculator, Desmos has been my favorite, sorry, GeoGebra. So they were calling this what? I, x, use x here. Equals, I want to graph this just to see if I'm doing a good job. Power 0.079x. And then what is 0.079 times 5,395? So then I can clean up my derivative, call it I prime maybe, or I dot, since we have a t here. That would also be an OK notation. Dot IDT, lots of ways we can call it. And was it 395? Oh, I forgot, I got lost in notation there. Yeah, 395. So the derivative is now 395 times e to that same power. And we want to evaluate the derivative 9 days in. Just plug in a 9. Up there. Calculator. So we got a 395 times e raised to the power 0.079 times 9. That did not end up in the power, so carefully use your calculator correctly. These for the power. And we'll test to see if that's right, because that parentheses wasn't obvious at first. So it looks like about 804, I would say. Oops, back here. this is approximately 804 people per day. And I could even do a better job by writing a sentence. 9 days into the outbreak, number of infected people, right, my Y value, is increasing by about 804 people per day. And then we need to check if we're right, because we really don't know if we did that right. We could have totally screwed up on the calculator there. So I'm just going to graph a tangent line. And so we need a Y value, right? So we just plug in 9 to the original function. What is I evaluated at 9? And so I'm just going to approximate it, even though we could take the exact values. So if I were to graph Y equals 10, Y minus, sorry, point slope form, 10,180 equals about 804 people per day times x minus 9. And then we just have to zoom in on that point. So we got to change our scale to get this Y value and the x value 9. So we configure, don't need negative numbers really, but we do need the Y to go way up there. So let's go double that to like 20,000. And what we should see is roughly a tangent line. And again, I approximated the slope. Let's get, oh, 9's way over there. Scoot over. Yeah, so that looks pretty tangent at 9. We could plot the point just to be sure. 9, comma, I of 9. And if we zoomed in really far, we'd find it's not quite tangent because I approximated the Y value and the slope. But zooming out this far is close enough, and for the purposes of like reporting how the rate of change is going, stating the whole number of people per day makes more sense than a fraction of a person. Because we're talking about people here. All right, so what else do we have? That's that one. Number 7. A ball is dropped from a height of 89 feet. Good question. So we did one like this way back in section 4, I think. Rates of change. And we want to know, when does it hit the ground? What's the instantaneous velocity and what is the average velocity? What's the difference between instantaneous and average? Does anybody remember? Instantaneous versus average velocity. Help me out here. Instantaneous is the limit. Yeah, so instantaneous is the limit, which is the derivative, and average is just the slope between 2 points. So find 2 points, find the slope. That's average. Because we skip everything in between, right? We're kind of averaging out what happened in the middle. All right, let's get a new page. Excellent response there. Thank you. And I think I want a screenshot of this because I want that graph. So I could just redraw it. They give me some nice information. I will just grab it. All right, so they kind of show me in the picture here where it hits the ground. So right before 2.5, so that helps make sure I don't mess up my calculation because I got a hint at the answer there. So we want average and instantaneous velocity here. We want a velocity function. And I just want to remind you about that. When it hits the ground here, the instantaneous velocity is the slope when it hits the ground, right? So it's that slope of that red line. Average velocity from when it started to when it ended is this secant line here. Okay, so the average is the green line here. Average velocity is green, and the instantaneous is that tangent slope. Instantaneous velocity. So if we want to find the velocity function, our instantaneous velocity, we just take the derivative with respect to time of our function s. So that's s prime. And in this case, 2 times 16 is 32, so negative 32t. And you may have seen this in physics class or some other class, that negative 32 is the force of gravity pulling stuff down, changing velocity, negative 32 feet per second squared. All right, so we got that right there. So then the instantaneous velocity when it hits the ground, ooh, we don't know what time it hits the ground. We better find that. So when does it hit the ground? Well, that would be position is 0, ground. So if we take our negative 16t squared plus 89, set it equal to 0 and solve, subtract that 89 over, divide by negative 16. And so t is the square root of 89 over 16. And I don't need to worry about the plus and minus because the minus would be before the ball got dropped, which is irrelevant. So it's just the positive square root. We can clean that up a little bit. Square root of 89 over 4 and 89. Can't think of any easier factors of that. I doubt that simplifies, but we could check. And then we want to approximate that, make sure it is a little before 2.5. Screen, Desmos. And graph this here just to make sure s of x equals negative 16 squared plus 89. Check if I take the square root of 89 and divide that by 4, do I get the right value? About 2.4-ish, which should be this point right there. 2.358, same number, so we nailed it. So that happens at about 2.358 seconds. And so then, so this would be the answer to part A. It hits the ground at was dropped. Instantaneous velocity, we just want to know, hey, what is v, switch to red for instantaneous, what is v of 2.358? And really we should plug in the exact value, so v of the square root of 89 over 4, which is just negative 32 times that, so we don't need a calculator yet. So negative 32 times the square root of 89 over 4. 4 goes into 32 8 times, so it's whatever negative 8 times the square root of 89 is. And the negative makes sense, right, because it's going down. Its speed is increasing in a negative direction. Let's calculate that. So we think the instantaneous velocity is negative 8 times root of 89. So about negative 75 feet per second. Negative 7, let's go with 3 decimal places again, 472. Yeah, that's velocity. Yep, so feet per second. And then the green one, so that's instantaneous. Average velocity is just the slope from this point to that point. So the average is change in y. We started at 89 and ended up at 0. 89 happened at 0 seconds, the start, and then minus the time we hit the ground, which is the square root of 89 over 4. And so that's going to be the average velocity. So what's that give us? That's going to give us 89 over negative square root 89 over 4. And we could rationalize that part right there and multiply by 4. So we're going to get negative 4 times the square root of 89 when we clean that up. Yep. Check that too. So 4 times the square root of 89 should be the average velocity, which notice it's about half of the instantaneous velocity, which makes sense when we look at the picture back here. You can see the red line is steeper, and it turns out it's twice as steep as the green line, which is interesting. So let's check to see if that's really the case by looking at the graph more carefully. So let's see, I just need to look up higher here so I can see that 89. So let's go up to 100. And then we don't really need to go up to 10. Let's go up to 5 maybe. And start at -1 perhaps. All right, so there's our graph right there. So if we graph the line, our average, which we just found, the y-intercept is the same as this y-intercept. So that line would just be y equals the slope we found above, -4 times the square root of 89 times x, our slope, and then we shift that up to have the right intercept, 89, and yep, nailed that. And then if we check the tangent line, we would do point slope form based on, yeah, here's our x value and here is our slope. And yeah, so that one's not bad. Y minus 0, right? That's the y value down here at this point for the tangent line. Don't really need that, but our slope was -8 square root of 89 times x minus that x value there, which was the square root of 89 over 4. And you can check this with approximations like I did before. It should work out okay, but exact values work too. So here we can see that tangent line right there to the curve. So it looks like we did good work there. What did we get? -37.736. All right, cool. Number 23, moving along. We've got to find the slope of the tangent line to this curve, and nicely now, Desmos and GeoGebra can graph things like this. Those old TI calculators and Cassios that were popular forever can't easily graph that, and we can't easily solve this for y without some fancy cubic manipulation. That's a little bit more complicated than a quadratic formula. So this is one where we can't easily solve for y, so we have to use implicit differentiation. Only way to do that. This is a cute graph, so let's graph it. Let's see, we have a 3 and a 2. Desmos, oops, wrong one. I have to calculate these. So x squared minus xy. Oh, I missed something. Was there there's a 2 and a 3 in there? What was it? 3 and then a -2. -3, -2. All right, my sign's all messed up. -3 plus minus 2y third, and that is equal to 0, right? Okay, so there is our function, and let's double check I got that right. Looks right, and they claim it has the point 1, -2, so we make sure that's the truth too. So let's check. It looks about right on the graph. 2, bang, that's on the graph. So we want to find the slope there. So we've got to use implicit differentiation. So we can't solve for y in this case. Negative 3x squared plus xy minus 2y squared equals 11 is our original function, and we want to take the derivative with respect to x on each side. And this is called implicit differentiation. The y is cubed. Yes, it is. Thank you for correcting me there. Good job. So this is called implicit differentiation when we take the derivative of both sides, assuming y is a function of x. So that's important. Implicit differentiation assumes y is a function of x, which means when we see a y, we got to think chain rule because y is a function of x. It's not x. And again, chain rule applies. Anytime you take the derivative of something and it's not just an x, then you have to apply the chain rule. And y is not just an x. So the derivative of negative 3x squared, power rule, gives us negative 6x. Here I have a product, so I have to apply the product rule, which says the derivative of the first x, well that's 1 times y, plus the first function x times the derivative of y, which is just f prime of x or y prime. So I'm going to call it y prime here. And then we have minus the power rule, 3 times 2 is 6, y squared, and since that's not just an x here, it's a y, implicit differentiation, chain rule says you got to multiply by y prime. On the other side, derivative of 11 is 0, and then we just solve for y prime, because we want to know what the slope is. Two ways to do this. If this is really complicated, and I did one of these a while ago, I would just plug in the point, 1, negative 2, right away, and then solve for y. It makes the work easier. And in this case, the question says what? Find the slope. It doesn't actually say find y prime or f prime of x. So we can make our work a little bit easier by just plugging in 1 and negative 2 here for x and y. So that's going to give me negative 6 times 1 plus y times negative 2 plus 1y prime, and then negative 2 squared is 4 times 6 is negative 24, y prime equals 0. Combining like terms, we get negative 8 minus 23y prime, add the 8 over, divide by negative 23. So we think the slope is 8 over negative 23. And we really should check this by finding the tangent line. So since we have the graph of the function, we can easily graph the tangent line, which would be y minus y1 equals negative 8 over 23 times x minus x1. Graph and see if we did a good job. So simplify it a little bit. Y plus 2 equals negative 8 23rds times x minus 1. Oh shit, both minus 1. Yeah, there it is. So that looks pretty tangent there, and we could zoom in to see that it looks pretty tangent. So I think we did a good job there. Graphically, it looks nice. And that's pretty much the only way to check it. All right, you guys are asking good questions and very relevant questions, I see. I'm glad you're looking at the exam. Let's see, 11 and 8 from the same set, I'm assuming. That was 23, so let's go 11. So here we have a power rule. Yeah, don't expand that out. What that means is don't multiply this by itself 12 times. Don't do that. Okay. Screenshot that. I mean, you could do it, but it would be very painful. as much fun as algebra is. Sometimes algebra can be painful. Not necessary. All right. So the chain rule applies here because there's a power out here, but the base is not simply an x. So a lot of times with chain rules, I'll identify what's the outer function, what's the inner function. So let's do that. The outer is whatever to the 12th, and that contains this inner function that is negative 3x to the 5th minus 8x to the 9th. That's right. And then the 5 is just a multiple tacked on, and so that just gets carried along. Hopefully remember to put it back in. Sometimes I'm forgetful about that. So f prime, let's not be forgetful and put the 5 in right away. And then the chain rule says take the derivative of the outer function, which would be 12 times the parentheses to the 11th. Leave that inside alone temporarily. And then multiply by the derivative of the inner function. So now I do that. So that would be 5 times negative 3, negative 15, 9 times 8, so x to the 4th. It's negative 72, x to the 8th. And let's see, what can we do to clean this up? Not too much. I suppose we could factor a negative 3 out of here. So what would that give us? 3 times 5 is 15 times 12 is 180. Check. 5 times 12 is 180. So we get, so I'm factoring a 3 out of here, just like dividing, right? So that's going to give me negative 180. And then times, there's not much I can do with that, just leave it as it is. And then we have this other one, so negative 3 goes into 15, 5x to the 4th. Plus negative divided by negative is a positive. 3 goes into 72 24 times. Yep. And then definitely ain't distributing anything here back in. So that's just, I guess we could have pulled out next to the 4th, but that doesn't make things much better, does it? Negative 180 x to the 4th. Maybe I'll write this up front. That leaves a 5 plus 24x to the 4th. There's that much less ink, a little bit, barely. So, yeah, so looking at this, that could be cleaned up a little bit. So if this were on the test, you wouldn't get full credit for that first one, but it's pretty good. That's a pretty good response there because you got the inner outer stuff right. So then either this one or that one. So this is okay, not great. This one is good. This one is great as far as answers go. I will be looking at the degree to which you simplify stuff or try to simplify stuff on the exam. So please write down nice, neat, good work. That's all we had to do. Yeah. Next, we got that derivative. And again, the expand means, like in this case, take the 12th power, which means multiply 12 of these together. Or in this one right here, multiply 11 of these together and see what you get. There's no shortcut for that. It's just a mess. You can kind of apply the binomial theorem that we talked about back in the beginning of this chapter, but again, don't do it. Not worth the time. All right, number 11, that was 11. Number 8, what we got? Oh, good, trig function. I was hoping you guys would have at least one trig function in here. 3 times the tangent of x over x. So this is a quotient, and there's really not much we can do about that. So do it. So we want to know what is the derivative with respect to x of 3 times the tangent of x over x? And this is a quotient, and we're kind of stuck with the quotient. There is kind of one trick, so alternative to using the quotient here, but that doesn't necessarily make our lives better, would be to rewrite that x in the bottom as an x to the negative 1. So I could say this is 3 tangent of x times x to the power negative 1, and then I get to use the product rule instead. So that would be an option. I'm going to use the quotient rule because it's good review. Quotient rule says if you have f over g and you're taking the derivative, it's the numerator derivative times the denominator minus the numerator times the derivative of the denominator. And remember, it's always a negative derivative of the denominator, which is related to this x is x to the negative 1 in the bottom, all over denominator squared. So applying that to this blue thing here, the derivative of the tangent, anybody remember that one? Derivative of the tangent, good one to have memorized. Come on, yeah, nailed it, Evan, secant squared. Now the 3 is just a multiple, we'll keep it with the tangent, so that would be 3 secant squared times the denominator. And then minus, we leave the numerator alone, 3 tangent of x, and multiply by the derivative of the denominator, which is just 1. Which sometimes I write, sometimes I don't. And then all over the denominator squared. And then we try to clean it up if possible. So the 3 factors out, which is a little less ink. So I get 3 times this fraction. Secant squared of x times x. Maybe I'll write the x in front there. So then I have a minus the tangent of x. And this x times the secant squared means trig identities aren't going to be able to do much to combine in some way the secant with the tangent. Thinking, yeah, that x in front makes this a little bit more complicated. So even if we were to do something like use what is secant squared 1 minus tangent squared, is that right? But we still have the x there, which means we can't combine anything with this tangent. So I'm thinking this does not clean up anymore. So anytime trig stuff comes out, make sure you get out a table of trig identities and think about it for a minute. So let's just think about that for a minute. I think that x times the secant squared just makes this impossible to clean up. Purple math, Wikipedia, SOS. Let's try SOS today. This looks like a very old website, 1990s-ish. All right, so I was thinking secant squared is 1 plus the tangent squared, but then we have that x times there. So even if I tried that, I don't think it's going to lead anywhere. So I'm going to try it anyway. But I think I'm going to circle this. I think this is probably the best answer right there. The Space Jam website, oh really? Interesting. Yeah, this is an old one there. Anyway, all right, so 1 plus tangent squared. So back here, we can replace the secant squared with 1 plus tangent squared, but it is times an x. It's still up, someone's paying for it. Oh wow, yeah, this is the truth. Someone's paying for it. So the 3 is just out front, times my fraction, and then I'm replacing the secant squared with a 1 plus tangent squared, and then I have to multiply it through the x with that. So that would be, instead of a 1, I'd have 1 times x plus x times tangent squared minus the tangent. And often with trig identities, you use more ink at first before you use less. And what did I just do right there? Oh yeah, because I'm replacing secant squared with 1 plus tangent squared. So we have to distribute that x through to both parts there. So there's the 1x and the x tangent squared. And then, you know, sometimes you'd hope that, you know, something with the tangent squared and the tangent might clean up, but this one has an x and that one doesn't have an x. So not helpful. Yeah, I think this is probably the best we got. All right, let's see. Looking back at the chat, that was the last question I got from you all. Any other problems you wanted to take a look at? Number 27, certainly. Yes, so my recommendation on logs yesterday, if it's not ln, is to rewrite it as an ln is the easiest way to do it. Otherwise, you have to memorize the formula. So for log base 5 of x, and oops, let's go back a second. It wanted, oh, then to plug in 8 after. Okay. For log base 5 of x. So I want to know what is the derivative with respect to x of 4 times log base 5 of x. And my recommendation was to rewrite this using the change of base formula for logarithms. So that means instead, we're going to call this 4 times the natural log of x over the natural log of 5. And the natural log of 5, that's just a constant. 4 is just a constant, so I can pull that out. So then I have 4 natural log of 5 times the derivative of the natural log of x. All right, see, I'll get what I'm doing there. I'm just using the change of base formula to rewrite that as ln, because the derivative of the ln is nice. We have a formula for that. That's just 1 over x. So then I get 4 over natural log of 5 times 1 over x, which could be written as 4 over, say, x natural log of 5, or 5 natural log, or natural log of 5 times x. The order you multiply doesn't matter, but that would be, oh, I missed something here. Oh, no, that's it, yeah. That's the derivative. Can I use less ink? I don't think so. So then they said plug in 8, so this is my f prime here, so f prime of 8 would just be 4 over 8 natural log of 5, which is 1 over 2 natural log of 5. Could use the power rule on that, but it doesn't really make it any better, and we can approximate it to see if we get the right derivative. So let's just do that for fun. And then I have a chat question I'll get to in a minute, Cole. Right? Yeah. Just want to throw this in Desmos for fun to make sure I got the right slope there. So my function f of x is equal to 4. And will this let me do log base 5 of x? Oh my gosh, it did. Cool. Anyway, to type that on a keyboard, Shift-6, the caret gives you a power, and an underscore gives you a subscript. So I just typed log subscript 5, and there must be a button for it here, I bet, in the function section. Miscellaneous, maybe. Yeah, log base A. So you can use any base you want in Desmos. If you didn't know how to type it, you can bring it up there. And then I want to know about the point 8 comma f of 8. Let's go away. So that's up there. And then I think I found the slope. So if I just do y minus f of 8 equals the slope, I believe, is 1 divided by twice the natural log of 8. Is that right? Do I have the right numbers in here? Oh, no, that's a 5 down there. So that was my slope times x minus 8. Yeah, that looks nice. We nailed that tangent line. So point slope formula is pretty handy in checking your work to see if you did do something right. All right, so then we have a couple more questions there. Let's see. Yeah, so you can send multiple files, so I should demo that, how to do that. So how to submit your exam, and then I'll come back here. So I think the easiest way, what I would do is after I write up all my work on paper, take some pictures with my phone, make sure they're clean, that they're readable. I have good light to take the picture in. And then there's a submit button on the exam, and that submit button gives you a couple of different options. So I'm going to go to student view, so I can see what you see. So once you're ready to, you've taken all your pictures, so then I would, from my phone, I usually email them to myself so then I can download them to my computer. It's easier than trying to access Canvas Submit on my phone. That's a pain in the butt. So I don't recommend that, but maybe you're good at that. I find it annoying and tedious and painful. So take pictures, email them yourself, download them to the computer, and then when you go to submit, what I'd recommend is you could upload a whole bunch of files here. So that's one option. So you just choose your file, add another, choose your file, add another. Or you can go to text entry, and if they're just images, you can just keep adding images, and then they display on the screen right here. So let me just take a screenshot. So I can just, I know. Let's just make believe this is my work. So then to get your images in, if you use the text entry, you switch over to Canvas here, and then My Files, and then that lights up the upload button. So then you can upload anything off of your computer. And so here, let's say that's some of my work there. So I upload it, and it doesn't matter about the alt text. As far as the image size, 1920 pixels is pretty much as wide as my whole screen. So you could leave it that way, or you could shrink it down. So I'm going to say let's make it 1,000 pixels. And it doesn't resize the file. All it does is display it smaller here. So if I right click on the file in your submission and say open in a new window, I'll see the huge resolution version of it. So this is just displaying it smaller, and then update, and then it'll throw your work in there. And then you can just do that again, throw in your next page, Canvas, My Files, upload, find your file, open it, change the size if necessary, and then can't get to my button down here. Really? There you go, update. I'm gonna put my next one in, and then I just keep going, insert file. So I think that's probably the easiest way to do it, but you can use it from the text, the file upload also. And if you do multiple submissions, Canvas shows me all of your submissions. So what I mean by that is if, let's say I'm done here and I submit it, and then a few hours later, I look back at my work on number 5 and I'm like, oh man, I could have done a better job on number 5. And so I clean it up and I take another picture and I resubmit. I will see all of your resubmissions, but you only see your last one. So if you were to resubmit just one more picture, when you looked back to see your submission details, you would only see the last picture you uploaded, not the 10 others you loaded before, which is kind of annoying. If you have any doubts about how your submission went, just write to me and say, hey, do you see blah, 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 and I'll go take a look. And if I look at it tonight and I say, oh shit, something's missing, I'll write to you and say, hey, something's missing here before I start grading it. All right, I hope that was helpful. And a couple more questions, 28, 29. I was cold when I got here doing all this math. I'm all warmed up now. Okay, x to the 5x. So this one says use logarithmic differentiation. There's a few examples of this in the book, and I did one yesterday. So let's do that. Excellent question. New page. And I mentioned the other day on a similar problem, when you have a function like this, x to the 5x, there's some confusion like which rule you should use. If x is the base and there's a power, you'd think, oh, I should use the power rule. But if the power is variable, then you should use the exponential rule. And so which one do you use? And it turns out, well, you kind of use both. And the trick is to rewrite it as follows. You let y equal whatever it is. And mostly this is useful when we have an x in the base and an x in the power. And then what we do is we take the natural log of both sides. So natural log of y equals the natural log of x to the 5x. And the point of taking logs of both sides is there's this lovely rule of logs that says if you have the log of a power, just bring the power up front and multiply it. So this becomes 5x times the natural log of x. So the natural log helps me separate the power from the base into just a product, and now I can just use the product rule, no problem on that. Now we also have to think implicit differentiation here because y is a function of x. So now I take the derivative of both sides. So the derivative with respect to x on this side equals the derivative with respect to x of that side. So natural log of y, 5x, natural log of x. So on the left side, derivative of the natural log of something is 1 over that thing. And the chain rule says if that's not just an x, then you have to multiply by its derivative, y prime. On the other side, I have to apply the power rule. So the derivative of 5x is 5. The product rule times the natural log of x plus 5x times the derivative of the natural log of x, which is just 1 over x. And that cleans up a little bit because the x's divide out in the second part. So I get 5 natural log of x plus 5. To solve for y prime, which is what I want, I just multiply y to the other side. So y prime is y times 5 natural log of x plus 5. Now remember, y is really x to the 5x, so I can multiply that in here. So x to the 5x times 5 natural log of x plus 5. And then as far as cleaning this up, I think probably the best thing would be to do is factor out this 5 here. You could distribute, I'm going to distribute the x through just to kind of show an interesting fact about this, but I think the simplest answer is f prime of x is 5 times x to the 5x times the natural log of x plus 1. And I factored that 5 out. So I would say this is probably the best reduced answer. And the only way you can check this is to graph this thing right here, pick a nice x value like 1 maybe, or 2, and see if this gives you the right slope at that point. If I distributed this through, so just a different version of f prime of x, that's kind of cute, is 5x to the power 5x, right? So I'm distributing that there, times the natural log of x plus 5x to the 5x. And let's see. Yeah, so we've kind of got two rules going on at once here. The 5 came down here, right? Kind of like the power rule, although we didn't get to reduce that by 1, but it's similar. And then the whole natural log of x times x to the 5x is related to the rule about bases other than e. So remember, the derivative with respect to x of anything, any base b to the power x is equal to the natural log of b times b to the x. So that's the general exponential rule there. Okay, 29, and then we're out of time. Yeah, so 29 is similar, and I think I did this problem in class yesterday, didn't I? Or I did one almost exactly like it. Let's go for it. So it's a lot like this one right here. Oops, wrong button. Page is there. So I've got y equals 1 plus x to the power 1 over x, and we just apply that same procedure. We take the natural log of both sides. And And then the logarithm lets me bring that power out. So now I turn this power problem into a multiplication, which is not as much of a problem. And then I take the derivative of both sides. So the derivative of the left side, derivative of natural log, is 1 over whatever chain rule says multiplied by y prime, because that's just not an x, right? I'm taking the derivative with respect to x there. And y is a function of x, so there's the chain rule. On the other side, I'm taking the derivative, and I have to use the product rule. So let's see, the derivative of 1 over x, let's write that off to the side here. Easiest way to think about that one is to rewrite it as x to the negative 1. And so then its derivative is negative 1 times x to the negative 2, which you could also write as negative 1 over x squared. So derivative, and we could have used the quotient rule too, but I'm just going to go with this route instead. And yeah, I'm going to use this version of it here. So the derivative of 1 over x is negative 1 over x squared times the natural log of 1 plus x. And then we have plus the first function, 1 over x, times the derivative of the second, which is 1 over whatever was inside, times the derivative of what was inside. The derivative of 1 plus x is just 1, so the chain rule is applied, but doesn't really change much. And then we clean that up and multiply by y. So let's see, does that clean up much? I've got a negative natural log of 1 plus x over x squared equal or plus, excuse me, uh-oh, my battery's low, I thought I discharged you, plus 1 over x times x plus 1 or 1 plus x. I guess we could go for a common denominator by multiplying this by x plus 1 and this by x. I don't know if that makes things any better. So that's going to give us, I think I'll write it as negative x plus 1 times the natural log of x plus 1 times, plus, so that's this part, plus 1x or x all over x squared times x plus 1. So that's an alternative to the blue. Does that use less ink? Maybe. And then we haven't solved for y prime yet. We have to multiply by y. We still have 1 over y times y prime. So multiplying by y, I get y prime is this 1 plus x to the power of 1 over x times that crazy fraction, x plus 1, or that sum. Natural log of x plus 1 plus x over x squared times x plus 1. And we could clean this up a little bit more because this is the same base as that right there. And if you divide things with the same base, you subtract the powers. Is that really better? I'm going to write it and see. So out front, I would have an x plus 1, 1 plus x, they're the same, to the power 1 over x minus 1. And the minus 1 comes from this one in the bottom. Times negative x plus 1. Yeah, this is just a tough one. So I think there's multiple versions that use around the same amount of ink. This uses a slightly less amount of ink than this one there. But don't forget, we've got to multiply by y to get y prime. And this one, I hadn't quite done that yet. Yeah, so I guess that's the answer right there. And you could tweak it a tiny little bit more, but I don't think it's going to simplify much more than that. I'm not really seeing anything that uses much less ink. All right, that's it for fun with math today. On your exam, write stuff down neatly and numbered, and then make sure you have good light when you take your pictures to upload them. Sometimes I have students, instead of putting one file at a time in that upload, they'll like put them all in a Google Doc, one picture on each page. So that's another possibility to put it in one spot. It's up to you. And just message me if you have any questions. Have a great day.